Thank you. My talk is about orchestrating a fire sale, or like Die Hard-like scenarios, for bringing Dutch alarm systems to their knees. I found some crucial vulnerabilities in the way that alarm dialers communicate with the ARCs, the alarm receive centers. And that's what I'm going to talk to you about. First, I'm going to talk a little bit about me. I'm a reverse engineer. I stumbled upon this by accident because I was just reverse engineering this. In my day job, I work at NICAF, the Dutch National Institute for Subatomic Physics, where we do, I do projects for supporting physicists on the grid. What? That's interesting. I'm a free and open source software developer. I've worked at Samba in the past. I've been patching Linux kernel and a lot of Debian packages, have my patches. I'm also the co-founder and treasurer of BitLayer. That's the hackerspace in Amersfoort. And that's actually where I started this project on, because we have an alarm system. And our alarm system reports to the alarm receive center, but I actually wanted to get all this information as well. So why are they the only ones who get these events? I wanted to have these, to log them and to see what the hell is going on at our hackerspace. If someone's breaking in, I want to know. And I want our community to know that somebody's breaking in, because someone in the community has got to be in the neighborhood to check it out. So we broadcast all this on IRC, and that's actually working right now. So let's take a look at the protocols. So what is out there? For those not familiar with alarm systems, there's a couple of legacy analog protocols. Actually, there's tons more variations, but these are the most important ones. The SIA, and there's the extended SIA for analog, and there's the ADEMCO contact ID. And all the other protocols are actually evolved from the analog protocols. On the IP landscape, we have CIHS, that's HS for highly secure. It is not. We have Vebon SecIP. That is a protocol that actually tried to implement good crypto, but failed in quite a bit of what they were trying to do. Now, there's the Chiron proprietary protocol. That's not really all that leaky, except that they have the option to turn off encryption, not working. And then there's the ADEMCO IP protocol, which is very simple. I have not actually looked at it properly, but I've seen several messages that were completely identical, so I know it's not good crypto. So I'm gonna check that out later. And there's the American standard and the German standard, which I have not looked at all because I have to pay for the standards. And I don't want to do that. So there's a fatal problem with the industry. There's a couple of fatal assumptions that are made, a couple of fatal mistakes, and I'm going to talk to you about two protocols, the SIA-HS and Vebon SecIP, and how big the problem really is. But first, I'm going to talk you to a couple of assumptions that seem to be going around in the security industry, or at least the non-digital security industry. Well, one of the things they were actually actively trying to do, the same for the PIN, is like, okay, I can have a secure connection just by setting up a certification policy for internet service providers. So if I certify the internet service provider that they have secure communication or some sort of their good enough infrastructure, and then I'm gonna peer with them directly, and then everything must be secure, right? No. That's not how the internet works. You cannot trust a packet on the internet. So if you certify an ISP, it's not going to help. You have to treat the entire chain as being untrusted, which they're not doing. Well, source headers can be trusted. Well, I've seen this assumption in a couple of protocols. If the source IP matches, it must be legit. No, it is not. It is not an analog system anymore. You cannot trust the caller ID. And even in the analog world, you couldn't trust the contact ID anyway. Bad. Well, apparently they do not think a session can be hijacked. So they assume that on the internet, packets are from the same peer, which is incorrect as well. Yeah, I don't think I have to explain that to this crowd. This one is actually pretty interesting. If I have a proprietary protocol and I use some fancy encryption, which my electrotechnics came up with, nobody can decode this. It's going to be secure, right? Well, no. The Alphatronics product catalog specifies that it's impossible to decipher the message using their SIA-HS protocol. Well, we're going to look at it later and see how secure it really is, but I can guarantee you it is not impossible. But I like to do impossible things before breakfast anyway, so. Yeah, certification, very interesting. So the security industry works a lot with certifications. If you have a certificate on your product, it means it's secure. No matter what vulnerabilities are in there, as long as the certificate's on it, and the assurance companies are happy, and the product will be good enough, it will be secure. In fact, the Alphatronics send out a security bulletin to their customers saying, we emphasize that the uncovered vulnerabilities do not influence the product certification. Really? Interesting. So the certification actually means nothing. Exactly. It doesn't mean anything. It does not mean it's secure, which they assume that it is. Same for this proprietary protocol. I mean, if I send a packet and I craft it a specific way and the other side can decode it, must be impossible for others to do this. Yeah, no, that's not true. We can reverse engineer this, no problem. Same for this one. If it speaks the same protocol, it must be a valid peer. So if I can establish a communication, we actually speak the same language. The other side must be trusted, right? No. Wrong. This one is actually one that was made by Vebon for their SecIP protocol. They have implemented crypto. They could have done it right, but they almost got it right, the encryption, but they did not actually verify who they were sending it to. They did not do identity checks. So basically, we're doing RSA security and using that to send out an encrypted AES key for the session key. So if they would have done it right, they would have a secure connection, but no way to know who they were talking to. Incorrect. Encryption is not enough. This is actually the Chiron case. If you are a security company and you give your alarm centers the option to disable the encryption, you cannot assume that they're not going to do this in a live deployment. I've actually seen alarm receive centers operate without encryption, and the encryption in the Chiron protocol is also the identification, because they use a rotating key, and it would be secure if it was enabled, because the key was only known to the other party, and if the key matches the encryption, you would have at least know that the other side has the proper key. But if you're going to turn off the encryption, you're actually making the entire protocol anonymous again. And this is actually a live deployment right now in the security industry. Yeah. Apparently, it is easier for the alarm receive centers to have their technicians that are on site just plug in something and configure the IP and say, oh, okay, now it's secure. But it's not. And just enable the encryption, make sure the other side configures a key or whatever. But turning it off, bad. Don't have this option. And the final assumption that are made is like, if you are an alarm system electronics engineer, it does not mean you understand internet security. It doesn't mean you can't design it, but you can assume that you can. Internet security is a business. If they would have used something like SSL for a secure communication channel, they would at least offload this to a library that would actually do all the security for them. But the way it's implemented now, everybody is doing their own sort of obfuscation methods, and it's actually not secure in any way. So don't have your electronics engineers design your security. Have security engineers design your security. Well, let's go through the alarm dialer basics. There's a couple of acronyms in my slides. I try to limit them, but there's a couple I cannot really avoid. There's the ATE, that's the alarm transfer equipment, or I'm trying to call that the dialer as much as possible. The alarm receive center, which is basically the operator on the other end of the alarm receiving, and that one is actually the person that's going to call the police if there's a problem. There's a prom key, that's a unique account code for a building, that's sequentially handed out, so that's 1 to 10,000 prom codes for any given protocol. The ATE is the dialer, it sends out the alarms. ARC just sends basic acknowledgements. Another thing you should know is that inside the protocols there are SIA codes, and that's 2 character codes. That's like burglary alarm, burglary restore, tamper alarm if somebody's tampering with a sensor, or the panic alarm, which is the robbery button. If you're a bank and you have these at every counter, if you press it, an alarm is being sent out to the alarm receive center saying panic alarm. And if you want to restore this, you have to have a key to actually unlock the button, and then the panic restore is being sent out over the wire. Well, let's look at the first protocol. SIA highly secure. It's a protocol designed by Alphatronics for their own products. It was designed, I think, in 1993, 1992. It's impossible to decipher according to the 2013 catalog. Well, let's see how secure it really is. So, I don't know how many of you can actually read this, but if you have seen this presentation before, try not to speak. But can anybody guess which cipher this would use? Just yell. Okay, tough crowd. That's okay. You are looking at a packet. This is a packet that's being sent out from the dialer to the protocol. This is actually a protocol dissector you're looking at. It's called Wireshark. And this is basically a basic IP header. And from the highlighted parts, what the hell? Okay, from the highlighted part, that's actually the protocol part. So one of the things you'll actually see is that there's a repeating pattern in here. We see here that there's a lot of B6, 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 B6 going on. This means that this is not proper crypto. It cannot be a proper crypto. My first instinct when I saw this was, okay, let's try and get this to a XOR cipher and try and XOR this entire string with B6. Well, I made a small script for this, just exporting the byte array from Wireshark, just paste it into Python, XOR it with B6. That's what you see here. And voila, we have a decipherable message. Some of them is actually not ASCII, so forgive me if so you can't read all the characters, but you can actually see that this is a registration request. This is actually the heart of the protocol. In this couple of minutes, we have actually broken the protocol already. I gave this presentation to a couple of security people, just about 30 of the Dutch security people. And actually that was just blurted out. People blurted out the key as well. I mean, this is not hard to do. It's actually very, very simple. So what you see here is that there's the ACLX 1.7. That is the dialer device name. And it's trying to register to the alarm receive center. What we also see is 1255, which is actually an incorrectly encoded prom code. They're encoding, this is actually a decimal value, and they're encoding it as hex, which is incorrect, but was making my life easier because I can just see in the hex that that is actually the prom code. So, thank you. Made my life easier. So, oh, okay. The return packet. I don't know if you can actually see this, but can anybody guess what key this would be? Excellent. We have now cracked the return packet as well. So we have the registration renewal request, the registration renewal, and it's directing it to a different port for the rest of the communication. But this is actually the heart of the entire protocol. It would just give out the SIA code in this session this way, and it's not really secure. I mean, I would not say in my product catalog that this is impossible to decipher because, well, we've deciphered the return packet pretty quickly, didn't we? So what do we have? We have the packet length based in the first part of the packet, first 4 bytes. Then we have the device name, that's actually XORed. We have the decimal prom coded, encoded as for hex. We have the actual message, which is an ASCII string, giving away everything. And then we have a checksum. Okay, the checksum was a bit more work. Because, well, I was thinking a bit too hard about this. I was seeing a 16-bit key, and I was trying all the algorithms like CRC and all the CCIT values, CRC10 to CRC16. I was like, shit, why doesn't this work? Well, then I just put all the messages together and I saw, well, larger packets seems to generally give higher checksums. I think, this is odd. A checksum shouldn't do that. But it must be either multiplication or addition if it's getting higher with the increased packet length. So I was like, oh, maybe it's a sum of all the bytes. Yes, it is. It's not actually a checksum. Shit. So there we go. That's the entire protocol, just in a nutshell. I have a code online for this protocol. The CIHS ARC implementation, I do not have the exploit code for this to actually send out alarms, but it's very possible to do. I have a SecIP ARC implementation already, which is the other protocol we're going to talk about just a little bit later. And I have some pluggable database event handlers and JSON bot IRC notification. Already working on the Chiron Iris Touch implementation. That's a proprietary protocol. I'm still working on it. I can tell you that it does use MD5 sums for every packet. The first checksum is the MD5 sum of the previous packet, so we can actually checksum and check that the session is valid. And the rest is ARC4 encoded, which is not a strong security, but it still is impractical to decipher given the number of messages that are going out there. And the key is rotating every packet. So I think it's good enough, assuming the encryption is enabled, obviously. Okay, so this is actually what I'm doing at BitLayer already today. This is probably just too small for you to see, but what you basically see is opening report, closing report. This is IRC, just IRC client, and it would just give out alarm events. For example, here there was a burglary alarm. The burglary zone has been violated while armed. Hey, that's not right. But then we see that a couple minutes later, oh, I can't even read this, that the opening report, the account was disarmed, and then actually the burglary was restored. The condition has been eliminated. And this was all in the span of 2 minutes, so somebody was probably just too late entering the key into the keypad. That's okay. That happens. The rest you see just basically it disarms and arms. This is just a live implementation at our hackerspace of this protocol. So you can actually see that it's very possible to attack this and decipher this. There's a couple of things we should keep in mind when we're designing a protocol. We must protect it from packet injections. If we don't have, we could get some bogus data and we'll all be screwed. We need to have a strong cipher. We need to have strong encryption on these packets because they are sensitive. We can't have anyone faking this stuff. They have to be signed. We have to know that the actual packet came from the source that we know is the building that is being protected. We have to verify the identity. Otherwise it won't work. And we have to have forward secrecy. Is anybody here familiar with what forward secrecy means? Forward secrecy, I see just one hand actually. Forward secrecy means that if at some point the private key is leaked, you should not be able to decipher all the past messages that's being sent between the dialer or whatever the source and the destination. You need to have a session cipher like Diffie-Hellman that will make sure that the rest of the session is actually keeps being secure because that's not stored anywhere. You cannot, this key is not stored, so you actually have a session key that you're just going to throw away again. Because if you actually, for example, leak the RSA private key, in this setup, it will mean just replace the certificate, put in a new one, and you're fine. The past packets are, well, maybe you've lost a few while the key was being compromised, but anything before that, you cannot decipher, and everything after that, you can't decipher either. And that's a thing called forward secrecy. You can't actually just leak so you can actually leak the private key as long as you just replace it again. This protocol, however, I'm sorry, this is pretty bad. There's no identity verification in CIHS. There's no session protection. The interaction between the ARC, the Alarm Receive Center, and the alarm transfer equipment is completely predictable. This has some strong implications. One of them is because they're using UDP packets, I can send from my laptop a session from a source that I don't even have access to and set up a session because I know what the response is going to be. The handshake is completely predictable. I know which port I'm going to get redirected to, or at least I can guess. This way I can just attack an alarm system and actually not being traceable. Also, the PROM codes, the building codes, are completely predictable. There's 1 to 10,000. I can write a script that just sets burglary alarm on all of them. And that actually has some strong implications. I can do a man-in-the-middle attack. I can intercept the packet, send out only the packets that I actually want the alarm receive center to know about, if I just get in the middle. That's actually not the major pain in this protocol. The biggest pain right now is that I can send false alarms from anywhere while remaining anonymous. I can just have a script on my laptop that would just trigger an alarm at all the alarm receive centers, and they would go berserk. They would call the police on the first 4 messages, maybe the first 10 messages, and after that they'll start scratching their heads saying, why are all my customers in alarm? That completely negates the police response. This implication of this sending untraceable false alarms is that I can actually do a denial of service on the alarm centers, all of them. I can flood their screens. They won't be able to respond to a valid call out. There's not going to be any fire alarms anymore. There's not going to be a burglary response, and there's also not going to be a robbery response anymore. If 2 zones on a given client are activated, then the alarm is considered confirmed, because it cannot be a sensor malfunction. Because normally, if a sensor malfunctions, there's 1 sensor going off. That's okay. You'll just send the owner of the building to it, or the janitor, whatever, and check out why the alarm is going off. If you have 2 alarms, it means probably that there's somebody in the building. So that's a confirmed alarm. That means that the police is being called for that alarm. So you can actually just do a denial of service on the police response, because at some point they're going to stop caring about this stuff. And then you can pull off a big heist while nobody cares, because they cannot care because they don't actually know which alarm is valid anymore, which can have some pretty big implications. I mean, I don't know if anybody's seen Die Hard 3 with all the dump trucks of gold and keeping the cops busy on the other side. But, I mean, it works. If you just can keep the cops out of your hair, I mean, you have plenty of time to actually pull off your heist. No problem. It's very, very bad. But the problem is not that I can do this, because I won't. The real problem is that anybody can do this. I mean, I've looked at this protocol for 5 minutes, and I've already deciphered the crypto. Okay, maybe if you guys did it, you would take more time, I don't know. But it's not going to be days. I know it's not going to be days. This stuff is bad. It's really, really broken. It has to be fixed. It really has to be fixed. Then there's the other protocol. This is the branch organization of all Dutch alarm institutes in the Netherlands. They're united, and they have designed their own protocol. This protocol is from 1996, 1997, I think. Basically what they do is they send out the RSA public key of the alarm receive center to the ATE. The dialer, the ATE, then uses the public key to send out the AES 120 session key. Then you have a secure communication channel, right? It's supposed to be secure. Well, if they had done it right, you would have a secure communication channel if they didn't forget about this thing called secure cryptographic padding, which I'll not go into too deeply, if you don't mind. But it's not going to be secure. No. There is a secure channel, sure. But who are you talking to? You just don't know, because you're not storing the public key, and you can get a different public key for every session. You cannot store the public key. So you don't know who you're talking to. And again, that has some strong implications. Well, yeah, there is no identity verification in this protocol. And again, they could have done this. I mean, they were using RSA. They could have done this. Just store the public key, let the other guys send out their public key, let them sign something, and you know at least who you're talking to. That's what SSL does. Problem now is we can do a man-in-the-middle attack on this protocol because, well, we can just get in between, send out our own public key. We'll have a session to the dialer. Sure, no problem. But we can also send false alarms from anywhere because the identity of the dialer is not verified anywhere at all. Again, same problem. The protocol is basically set up that it trusts the messages that it receives. They were using insecure cryptographic padding. I don't know if you're familiar with this. Okay. If you're using RSA, you can only use, for RSA 1024, you can securely encrypt 117 bytes, but you have to have the rest with secure cryptographic padding. If you're using the first few bytes, they're not random enough. It's a modulo crypto, meaning that in the original spec, they were using the first byte as actually something significant. But you can't, because you always are going to lose that byte, because the first byte in the key is going to be the top for the entire protocol. It's basically just a division by the key, sort of. So it cannot be higher than the key on the first byte. But if you're going to use this for something significant, well, you're going to lose data. You're going to have to pad this with random numbers. They didn't. So the implication of this is also that we can do a chosen ciphertext attack. If we send out a chosen ciphertext, we can actually get the key, or at least get to the contents of the messages. Because, well, sorry, you're not using RSA the way it's supposed to. It doesn't work that way. And there's also no forward secrecy. They could have done this easily, just by adding a layer of Diffie-Hellman. But, you know, if I have the private key, I can decrypt the entire event history. Again, it's pretty bad. Same here. We can do a fire sale. The only real difference here is that my source IP is traceable because there is actually a session. The session is not predictable. So if I have to attack anything using this protocol, I would either give up my source IP or I'd use an anonymity network like Tor to attack this. I mean, it's not a problem. I can do this. It's just a little bit more difficult. Not impossible at all. It's a very real threat. So what happened? I reported this problem in CIHS in August 2012 to Alphatronics. I got no response. But I didn't have really time to follow it up. But I did have time to do another protocol, because that's fun. I reported that in September. I got no response. Just about 3 weeks later, we did a small-scale publication at Hack in the Random 2600L databox. That was actually the talk I referred to earlier, where we actually just did crack this protocol live on stage. That actually helped. Interesting. Okay, I have no clue what's going on here. Yeah, I think it's a problem here. Great. Interesting. Then in January 2013, I started asking the Dutch National Cybersecurity Center for help. And they actually have assigned a coordinator for this, to coordinate with all the branches of the alarm industry, the security industry, to help coordinate this. And well, the first response was from Alphatronics is, could you please remove your publication? I'm sorry, I can't. It was out of my hands at that time. Vebon and ANI, which is actually, ANI is actually the one who designed the protocol for Vebon. They responded well. They actually hired a security company because they realized that their electronics engineers cannot design the security protocol. They hired a certified secure to do an assessment, a full assessment of the protocol. They basically came up with the same thing I had already told them. So that was good for them. They had two sources verifying the same thing. They hired Pine Security to help fix the protocol. And there's actually a new version of the protocol available now. So kudos, that's good. Chiron actually called me later, and they told me, they offered me a fully configured alarm receive center to aid my testing of their protocol, which is really helpful. Thank you. But now there still is a problem. There are thousands, tens of thousands of unsecured devices out there. Most of them get maintenance once a year because there are boxes that sit in the buildings of all the customers. So they have to go drive in a car to every customer to update the firmware to load the new protocols. But the main problem with this protocol, as long as it's enabled, I can send the false alarms on the receive centers. It's no problem. I can do this. So until the very last one of their customers is patched, the protocol has to be enabled. So this is still a real threat. Anybody can send out these alarms. Yeah. How are they going to fix this? Well, they're going to have to upgrade all the firmwares everywhere. The alarm receive centers have to go first, and then all the customers. That's going to be done in the next few months in the entire Netherlands, just to fix this. In the meantime, they could have two separate systems, one for secure protocols, or not known broken protocols, to isolate them from the insecure protocols. So if you have an attack, one of the systems goes haywire, but the other one still has sort of reasonably trusted data. Because you can't trust the data anymore. They can't trust the data they're getting at all. It's all wrong. So yeah, my code's on GitHub. You can check out the alarm receive implementation. If you have specs on other protocols, give it to me. I am very interested. I also have some specs of my own from some other protocols. If you want them, I can give them to you. But if any one of you has a dialer, which I have not mentioned, I'm very interested in reverse engineering it as well, because this stuff really has to be fixed. So thank you. Check out some of the other products I'm working on. And are there any questions? No, it's not on yet.
Have you had a chance to look at the updated version of SecIP?
I have looked at the upgraded version, and it's actually looking pretty good. They have fixed all the vulnerabilities that I could see. Yeah, they've actually done a good job. I don't think I'm qualified to crack that. So it's good.
I was kind of wondering that you mentioned this very simple XOR attack with two numbers, and are these numbers always the same for every 2 points between client and center, or is there at least some dynamic behavior?
Okay. Yeah, I used to think so. When I gave my first presentation, I thought this was fixed. But then I looked at the firmware and I actually saw that there is a lookup table for every packet. It gets looked up, something in the header that triggers it. And the cipher is actually a rotating cipher based on some value that's set in the first 4 bytes of, or actually the 4th to 6th byte, I think, in the protocol. But it's hard-coded in the firmware, both on the alarm receive center side as on the ATE side. So yes, in real deployments, I've only seen these 2 numbers, but I know they can be other numbers. But I mean, it would be very, very easy to crack. Just do a statistical analysis or just look at the packet and it just falls apart. So yeah.
What is the time between authenticating yourself to the IOC? So if to say, I would say, yes, I am this alarm system, right after that the real alarm system would say it, would the IOC think that, no, the alarm central would think that I am the alarm system? Or how do they say?
No,
yes.
you don't actually have to, the timing is not even relevant. I mean, you can just trigger an alarm anyway, or submit a restore anyway.
But not triggering the alarm, just because it authenticates as well. It says, yes, I'm here, I'm fine, I presume.
No, it does not authenticate. Well, it sets up a session, but it does not really authenticate. So you can just create another session and send out a different packet. The timing is not even relevant.
And what is the lifespan of a session?
That varies. It's not defined.
Okay.
So until the firmware is rebooted or whatever, it's not defined.
And does the alarm central keeps the old session open? When I start a new session from another device, does it keep the old session open?
Okay, this is all UDP based. So it's not actually a session as such. There is a handshake in the beginning of when the device boots. And after that, it's just a matter of sending the alarms via UDP. So no, it's not, timing is not an issue or anything. It's just, you can send anything.
Okay, yeah, thank you.
You said you'd had a look at some of the firmware for these dialers.
Yeah.
First of all, how do you get the firmware? And second of all, have you had a look for any exploits in the comms?
I got the firmware mostly by pressing the upgrade firmware button on the device and just capturing the traffic. Because that's another problem. I haven't even mentioned this. When you press update, it will just contact a fixed IP address to get the update. It does this over an unsecure protocol. It's not signed. If you want to have your own code in there, just hijack that specific IP and send out false firmwares. Yeah. The only problem is you have to manually press the update firmware button on the device. But that's how I got them, just by capturing in Wireshark and just saving the entire dialogue and cropping out what's not relevant.
Questions? Excellent research, really cool. I know you mentioned just a bit about the disclosure part.
Yeah.
Can you elaborate just a bit more? How was their response? Were they hostile? Did they got more questions for you, or was it simply just accept your findings and thank you, that was it?
It was a bit mixed. Because it's actually two protocols, so there's two parties involved. Actually, there's more parties involved. So with some of them, I get the vibe that they were being annoyed. So why do I have to fix this? And isn't everything broken anyway? Yeah, not the proper response. But actually, Vebon and ANI just were very happy to accommodate this. And actually, from their point of view, it was, okay, very good. Now we can actually review the protocols that we have in place for this, because apparently there's no protocol in place for security incidents at the security companies.
That's the argument.
Yeah, so they were like, oh, actually, yeah, good point. We have to implement these protocols, and they were actually very happy that I reported them and not just started exploiting them, because I could have done that.
Anyone else have any questions? No. All right. Well, thank you very much, Wilco.